Today we look at how integers are represented in computer memory and 2's complement. When representing positive integers, things are fairly straightforward. It's a simple conversion between base 2 and base 10. Suppose we have 1 byte available for integer storage. 1 byte contains 8 bits, and therefore we can store at most 256 numbers from 0 to 255. Say we want to store 42, which breaks down to 32 plus 8 plus 2. This is your binary representation for positive 42. Additions with positive integers are quite simple as well. We basically follow the same principles as we have learned in elementary school. When representing negative numbers, things get a little tricky. There is no negative in computer memory, so we need to find a way to signal to the computer the sign of a number. The most widely used method is called 2's complement. Let's take a look at how it works. Suppose again we have 1 byte available for integer storage. This time it can be either positive or negative. 8 bits in this byte can store at most 256 numbers, but this time from negative 128 to positive 127. We will see why in a moment. Say we want to store negative 42. We first turn it into binary for positive 42. Then we take the 1's complement of the number by flipping all the bits in the number. Finally, we turn it into 2's complement by adding 1. This is how we store negative 42 in computer memory. Another way of thinking about this process is if the most significant bit is set to 1 with all other bits set to 0, it represents the most negative number those bits can represent, whose magnitude happens to be half of 2 to the power of the number of bits. So with 8 bits, the most negative number they can represent is negative 2 to the power of 8 quantity divided by 2. Which is negative 128. All negative numbers begin with the leading bit 1. To get to negative 42, the rest of the bits must equal to the difference between negative 128 and negative 42, which is 82. 2's complement is designed thusly to enable easy addition as well as subtraction. Subtraction can be performed by adding the negative value. Unless actual overflow occurs, no special treatment needs to be given to any of the bits. The leading carry digit can just be safely discarded. The same circuitry that can perform additions for positive integers continues to work flawlessly on addition and subtraction of signed integers. Thanks for watching. I'd like to give special thanks to Garlic, who did not sponsor this video. Kiss your partner after eating garlic to test his or her true love. This is an Indian Tribe production, all rights very much reserved.